Okay, so now I want to solve two different examples and show you an important concept. So we wrote this code to solve our benchmark problem using the analytic method and using the finite element method, right? Let's run the code. You can see the finite element solution, analytic solution, and mesh here. So also we solved this problem using ANSYS Maxwell software, right? This is the solution region and voltage on this edge and voltage on these three edges. So let's set number of adaptive passes equal to 25, for example, and run the simulation. So as you know, we say that the solver can converge when we have a convergence in the value of total electric energy stored, right? So we should have something like this iteration number here and the amount of electric energy after mesh refinement. So we have, when we have convergence in the value of total electric energy stored in the solution domain, we can say that the solution is fine enough. So you can see here in the first iteration, the total electric energy stored in the region is this number. And finally, after 25 adaptive passes, we reached this number. And we have a high difference between this number and this number, right? Actually, this is 4 times this number, 4 to 5, right? Times this number. So why we have this situation and why it is hard to solve this benchmark problem and converge? The reason is this. Here we have electric voltage that is equal to 1, and here we have electric voltage that is equal to 0. So the gradient of electric energy here is high, right? So you can see the mesh is fine and fine here in this area. So actually these two are our boundary conditions, Dirichlet boundary conditions. And as you can see here, the Dirichlet boundary condition on boundary of this problem is a discontinuous function, right? Here, when you plot the solution using the patch function, instead of using x and y coordinate, also you can add the z coordinate, and the z coordinate could be the value of electric voltage. So if I run this code, you can see the solution as a surface, right? So I can show you this surface. Let me write here axis equal, and you can see this surface, right? So this is the electric potential distribution. Here is 0, 0, 0, and here is 1, right? So the value of Dirichlet boundary condition is discontinuous, right? So when we have a discontinuity on boundary condition, Dirichlet boundary condition, the convergence is hard to achieve. Now let's use another boundary condition. For example, if I apply a boundary condition like this, consider this as x-axis and this as y and this as z. So this is our solution domain 1, 1. Now consider I apply 0 electric voltage here and electric voltage variation like this. For example, a sinusoidal function and 0 here and 0 here. So what if I apply this kind of boundary condition? So if I apply something like this, the electric voltage on boundary is a continuous function, right? Not a discontinuous function. So I can write here in the MATLAB code, here when I apply the Dirichlet boundary condition on top edge, actually here, f index equal to v naught. Instead of this, let me comment this and uncomment this. I can apply something like this. V naught times sine of pi times x coordinate of these boundary points, right? The x coordinate. So if I run this code, this is the finite element solution, right? And this time I have a continuous Dirichlet boundary condition, right? On my boundary. So if I apply the same thing here, instead of 1 volt on top edge, I can write 1 volt times sine of 1 sine of pi times x divided by 1 meter in the global coordinate system. And okay, so now revert to initial mesh and solve, analyze. So let's check for this case that we have a continuous Dirichlet boundary condition. The convergence is achieved in only 2 iterations, right? So this is important. You can see also the mesh, right? So when we have continuity in Dirichlet boundary condition on our solution domain boundary, the convergence is achieved in few iterations. So in electrostatic problems, when we apply fixed voltage on boundaries of the solution region of our problem, we should care about these kind of discontinuities, right? So even if I reduce the percent error 0.1 and run the simulation again, results, solution data, you will see that we have also convergence here again, right? So this is important that you can see the same thing here in our MATLAB code when we apply continuous Dirichlet boundary condition.